Let's look at a sunflower. A sunflower, when it starts to bloom, it looks like this and it slowly opens up in the middle. And in fact, in the center, you see a lot of dots, and that is actually what is technically the flower. The entire sunflower is actually a collection of these florets. And these arrangements follow something called the Fibonacci series. And Fibonacci series goes as follows. It goes like 1, 1, 2, 3, 5, 8, and so forth. And this particular ratio of certain arrangements inside a flower, it follows this equation: r is equal to c multiplied by the square root of n, and theta is equal to n multiplied by 137.5 degrees. And n is the nth floret, and c is a constant, and 137.5 is something called the golden angle, and we will address golden angle in a minute. But essentially, the spiral in which these flowers are arranged in a particular form, if you notice the lines that go through like this, it's in a logarithmic spiral that follows the golden angle, and we will come to that in a moment. If you look at these numbers, 34, 55, 144, and so forth, these arrangements essentially follow these 55/144 pattern, and that's how the golden ratios are arranged. And these are all Fibonacci numbers that it follows. Now, if we took this equation that tries to plot this particular set of r theta values, and we put it into a graph, and let's just go to the graph and say change its expression to this, and say that I want to see the polar chart. And now we want the line thickness to be very small and marker size to be very thin, so that we can actually see the arrangements of the dots inside of it. And here we can see the let's increase the marker size by a very little bit, and you can see that clearly there is a spirally pattern out here, and these are what we are seeing in the middle of the flower here. And if you take a picture from the Wikipedia, and we can look at the florets inside, this is a very interesting version of it. Let's make it the wallpaper for this particular session. A two direction of spirals arising from the middle. Now I've actually tried to manually plot this by hand using our InGrid app, in which I took this picture over here and I colored it slightly differently so I could see what's going on. And so I have counted like 1, 2, 3, 4, 5. These 5 spirals followed by another 5 spirals, another followed by another 5 spirals, another 5, another 5, and another 5. Then, so that will be altogether 10 plus 10 plus 10, 30 spirals. Then this is 31, 32, 33, and 34. So if you take this 1, 2, 3, and 4, so there is 30 altogether plus 4, so that is 34. And if you count it the other way around, it'll go like this. And here I'm again doing 5 marked and unmarked 5, 5 marked and unmarked 5, 5 marked and unmarked 5, and so forth. So it's all a total of 10, 20, 30, 40, 50, and then this is 51, 52, 53, 54, and 55. So this gives you the pair of 34 in one direction and 55 in the other direction. So this is how the sunflower, the florets are arranged. Now, when we do this equation, as you can see here, the florets basically show the same pattern as what you're seeing in this particular picture. So we discussed about the golden angle, golden spiral, and golden ratio as related. So what happens is that the Fibonacci series, if you took chunks of 2 of Fibonacci and you mapped each of them to get the ratio of consecutive numbers, you would see that it tends to a number that we call as the golden ratio. And now a golden ratio is essentially the ratio such that if you took a line that was of length a plus b, and if you took a segment of it which is of length a and the smaller segment of length b, if you divided the ratio a by b, And if that equaled the ratio of a plus b by a, that would essentially be the golden ratio. So that means there is an equation a plus b divided by a is equal to a by b. And if you look at it, and if let's say we call phi as the golden ratio, or a by b, you will get an equation. So it'll be like, if you divided this is going to be like 1 plus b by a is equal to a by b. And if we call a by b as the letter phi, this letter phi, essentially that means phi is equal to 1 plus 1 by phi. So if you took an equation like, let's try to do the real math on this. So you could call it that 1 and 1 divided by phi equal to phi, right? And if that's the case, and you could multiply both sides with phi, so this is going to be phi to the power of 2, and this is going to be phi square is equal to plus 1. And so if you took both to one side, you're going to get this equation, phi to the power of 2 minus phi minus 1 is equal to 0 as a quadratic equation. So that's what we are representing here. So if you had an equation such that it was x to the power of 2 minus x minus 1, and you try to solve its roots so that you could find, let's take this equation x to the power of 2 minus x minus 1, which is basically what this is, and find its quadratic roots algebraically. It'll give you this answer, 1 half minus 1 half multiplied by 5 to the power of half, which will be root of 5, square root of 5. So this is equal to 1 minus square root of 5 divided by 2, and this will be 1 plus square root of 5 divided by 2, and that's what they are having here. So if you took that expression and if you evaluated that, so essentially 1 plus square root of 5 divided by 2, so obviously we have to put this in parenthesis, and this is going to be this number 1.686180339887498995. Now this is actually an irrational number, so we have to switch on the ops dot on and evaluate at a higher decimal accuracy, and you will see that it goes, it'll continue to go to the right here. Now, so if you do evaluation at a higher decimal accuracy, you will get, golden ratio to a much higher length. And you see that the number of roots it has is 2. So there is 1 plus and there is 1 minus. So let's do both of them. So what we're going to do is, and do the 1 minus, and these are the two roots of the equation. So one is going to be 1.61803339, and the other one is going to be minus 0.61803339. Now remember that if you take the absolute magnitude of both, the difference is 1. So this is 1.6180, the other one is 0.6180. If you remove the 1 from the left, they're equal. Now these ratios appear all over the place. So if you take the golden ratio as the ratio of lengths, similarly if you took golden angle, it's also very similar in its definition. It's essentially, if you took the two angles, so if you took the ratio of A divided by B in terms of the angles, if that equals the angle A plus B, which is 360 degrees, divided by the angle subtended by the larger side. So if 360 divided by angle A is equal to angle A divided by B, that is called the golden angle. And obviously it is the same kind of ratio. So it's going to be 360 multiplied by 1 minus 1 by phi. That essentially adds up to 137.508. So we can actually do this math and just make sure that, that's how we have to think about it. So 360 degree multiplied by, so if this is the golden ratio, so let's take this golden ratio into GR1 is going to be this actual number. So let's say golden ratio to this combination of arrays, and you get the number here. So let's just assign these two expressions in the normal numeric computation, 1 plus square root of 5 by 2 to the golden ratio, and hence the golden ratio, the first element in here. So let's take that and take this ratio of 360 multiplied by 1 minus 1 divided by this. So that gives you 137.50764, and that's what the golden ratio is that you're seeing here. And in radians, so let's first define this in degrees and then convert it to radians, and you will see that you get 2.3999 radians, and that's what the golden angle is. And golden angle is seen all over the real world, starting from heads of state. The way that these spirals, this is a logarithmic spiral that is based on the golden ratio, whose growth factor is the golden ratio. And if you see lots of these images that are use the golden ratio or golden spiral or golden angle as its fundamental design, you would see that these are fairly interesting to the eye. If you look at the Apple logo, they basically have used this ratio of things. You can see that the increase in growth of these are based on the golden ratio. There are tons of examples on the web that you can look at, where the Mona Lisa, or the shape of the year, or the sunflower spiral, or the Greek architecture, and so many different things are based on this ratio of and many proportions. So if you use this proportion in your artwork or logos, or you can look at all these different logos like Twitter, and all of them use this particular ratio in very clever terms. Or you can even see this in terms of faces and architecture, and even the Vitruvian Man. You can see that the golden ratio is kind of essentially there. It's in the shape of humans and all kinds of shells, and you can see that the same sort of structure is there in the way it is shaped and so forth. And you really would see this in all over the place in terms of how it appears in nature. This particular combination of the golden ratio, golden angle, and golden spiral, as you have already observed, it appears in so many different places, and the values are, this is the golden ratio value, and the golden angle is in radians 2.399, or in terms of degrees it's about 137.50. So that is the angle that you would repeatedly see in these different structures and so forth. So and as we have already looked at, the different counts on these things are based on the Fibonacci series, which is related to golden ratio, and so they're all in one circle. In fact, the same Fibonacci numbers that we have looked at. So let's take the Fibonacci numbers here: 3, 5, 8, 13, 21, and so forth. So if you took a pine cone, I actually took this pine cone from the in one of my walks, and I picked it up, and these two spirals that you see here, this is actually 1, 2, 3, 4, 5, 6, 7, 8 to the left direction, and to the right direction you can see, let's start with the horizontal here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So as you can see, 8 and 13 are sequential numbers in the Fibonacci series. So obviously we are seeing this in all these different diagrams, as well as the sunflower that I again counted as 34 and 55. So if you look at these two, it's going to be 1, 2, 3, 34 in this case, in this direction, and 55 in this case. So 10, 20, 30, 40, 50, and 55. Sorry, in the other direction. So essentially, in a pine cone, you would see that in the two directions you get 8 and 13. So this is how you can see this angle and the golden spiral and the arrangements in nature. And as you can see, we are able to, using this equation, generate the pattern that you would see. It's called a Fermat's spiral, by the way. And essentially internally has this 137.5, which is related to this, as you can see, this circular angles and stuff like that. And when we do the plotting from 1 to 1000 points using ZCubes, you can see that they arrange itself in this pattern. That is what you're seeing in the middle here. And when we counted it, it is 34 and 55, which are actually the Fibonacci series 34 and 55. And just likewise, when we counted the pine cones, the 8 and 13 pattern. So 8 and 13, that's here. So this how all of these are connected together. Also, the proportion that kind of is pleasing to your eye, and that's why many of these buildings and artwork and all that kind of use it. It's probably because we feel the growth rate of certain things, we almost intuitively assume that it is going to be proportional to what we already have. And in that sense, they are kind of a natural way of thinking. And possibly that's why we find certain pleasantness in watching this ratio of things. And if you had to ever design a logo or something, you would rather go with these kind of principles so that it looks good, and we are something as pretty as a shell or something like that, which actually has that spiral form to go with.